So the first thing we'll hit on is if you want access to the cluster, make sure that your lab coordinator had requested it when you were onboarded, or submit a ticket and we'll get you set up, usually within the day. Because the cluster is a build resource, you do have to be added to have access to it. That way we know which lab the billing should go to by default for all of your jobs.
Rob, what is the best way to submit a ticket?
So currently the help desk ticket system is support@hhmi.org.
So yeah, just send an email with your request to that address.
Yeah. Assuming that the help desk hasn't changed in the intervening years since this recording, that's the place to go. If you get a bounce back, you can always check with your LC, and they should know what the current email address is to submit a ticket. So the first place that you're going to take a look at is this massive wiki page. It includes all of the information you could ever want and then some, but it is massive. So what we're going to do today is distill it down into a few of the starting tasks that anybody would want to do while getting acclimated to using the cluster. So the first thing typically is, how do I connect to it? In this case, I'm demoing on a Windows machine, mainly because it is the slightly more complicated of Windows, Mac, and Linux. There isn't by default currently a built-in SSH client on the terminal, so you're going to have to install typically PuTTY. It's one of the easiest. For that, is everybody else seeing the artifacts at the top of the screen?
Yeah, those look like the Zoom windows that are not being overwritten correctly with the background data.
Let's see if I can make them hide.
Alternatively, if you, that's much better already. And if you drag your full browser window just down like a very small amount, then it probably won't obscure anything too much. Yeah, we can already see almost all of the window.
Okay, cool. So a quick Google search for PuTTY, P-U-T-T-Y, will lead you to this website. You can download the full version of it. Here you're looking for the 64-bit x86. Because it's a bit of a pain to install under one of the help desk managed VDI instances here, asks a lot of questions. I've already done it. But now we're going to need to connect. So the first thing that you need to know is what one of the host names is. There are basically two types of machines in the cluster. There's a login node, which is used for a jumping off point. You're going to connect to it. It's the place where you will submit jobs from typically. And then compute nodes where the actual computation and work is done. Typically, you won't be connecting to those directly. You'll be bouncing through the login node first. So we have two of them called login 1 and login 2. And the full address, janelia.org. And if you want to keep it around, you can put in a name here and hit save, and then it'll be in the list. Also, if you load one of these and then make adjustments to the settings of that particular session, you can go back and resave it, and it will keep those settings for future usage. Typical things you might want to change is your scroll back window. I would like it to be slightly larger. And we'll go back and save that. Now, if we just open it, the first thing you're going to be prompted with on the first connection is hey, I don't know what the server is. Here are the keys that it gave me. Do you trust it? On the first connection, as long as you're on the Janelia network, either secure network for wireless, connected hardwired, or VPN'd in, you can trust that having entered that fully qualified address, that it's really the host that you're looking for. So you can then hit accept. If at a later time that were to pop up unexpectedly, it might mean that something is happening in the middle. Feel free to submit a help desk ticket, ask questions about it, particularly if you're off-site and connecting from a sketchy access point in a coffee shop somewhere. There might be something odd going on. So we're going to put in my own name.
Rob, quick question.
Yes.
On Windows, I noticed that there's a new feature with recent builds of Windows. They're bundling in OpenSSH. I was wondering if there's a strong preference for PuTTY over using that feature.
Nope. In my case, it's just I've been using PuTTY for a decade and a half. So
yeah, I as well.
So you're going to enter your username. There's no @, there's no HHMI /, just the username, and then your password. And if you write it correctly, you will be given this prompt. Basically just says that you've connected to it. And in the case that this host is down for some reason, you can always connect to the alternative login server, which is login1. On login1, you'll see a similar one saying, hey, you can connect to login2 if I'm not available. And a short reminder that says, please don't run computationally intense operations directly on the login. That would include high IO operations, large file copies, that kind of thing. Okay. So on a Mac or Windows, or sorry, Mac or Linux, you will typically already have a terminal application installed. On Mac, it's called Terminal. If you hit the Apple key so that you open up the search and type in terminal, it will pop you open to a prompt similar to this, but on your local machine. Similarly on Linux, there are a number of different terminal applications. Typically, if you search for terminal, you will find it. And in that case, how you connect is just slightly different. We're going to use SSH. And then it's good practice to put in your username and then give it the host name. And in this case, I have pre-shared keys set up. And so it didn't prompt me for the password. It will typically prompt you for the password. The reason that you want to put in your username at the host is depending on the name that has been given to your account on your local machine, it might be slightly different and it will default to using whatever that is, particularly if you have your own install of Linux. So, but now you've connected just the same as we did in PuTTY.
Can I clarify something?
Yes.
Rob just showed two things at once, really, for efficiency's sake, and because once you're on the cluster, you're on Linux, so you can use SSH. But really, there's sort of two different things that you learn from that one example, which is if you were beginning on a Mac or a Linux machine instead of Windows, you don't need PuTTY. You could have done what Rob just did from the start: open terminal, run SSH username at login node. To get onto the cluster to begin with. And then the second thing that Rob just showed is once you're on the cluster, you can hop between different nodes on the cluster by using SSH. So he switched from login 2 to login 1, and maybe this isn't a basic feature, but you can also SSH directly onto a compute node if you want to inspect what's going on that compute node, in which case it would be SSH username at, and then the identity of that compute node, which we don't need to necessarily get into now. I just wanted to clarify that if you were using PuTTY, for example, on Windows, like Rob started with, that second command SSH onto login one, that's not necessary to get working on the cluster. It's just a demonstration of SSH if you are working in Mac OS or Linux to begin with.
Yes. And to follow on to the connecting to a compute node to inspect what's going on. Definitely a use case for it. You wouldn't want to be running the actual application having SSH. That would be submitted as a job, but connecting to then look at what's going on to figure out a misbehaving process or really dig into what's going on a second by second basis is totally a reasonable use case. So this is a very basic way to connect to the cluster. Using the command line, you can submit jobs this way. You can monitor jobs. It does have some drawbacks in that you can't reconnect to an existing session. You can reconnect and look at jobs that are out and running, but you can't really run something in this window and then disconnect from it and come back. So for that case, we've got a remote desktop software called No Machine, also named NX in the open source fork of it. And we've got it linked here in directions on installing the NX client right here. The important piece is what you're looking for is the No Machine Enterprise client. You can use some of the other ones. The Enterprise Desktop will include the client, but it will also set up your machine to do it and isn't necessarily required. So again, pre-installed to save us the watching an installer screen run through. On Windows, it's a simple wizard to install, click next through it, accepting the defaults. Similarly on Mac, it's a downloadable DMG image that you run through the installer and it puts everything in the appropriate places. Linux is slightly different depending on what flavor of Linux you happen to be using. But there are instructions on the wiki to go through all of this. So we've opened up the application and we're going to add a new connection. We're going to call it login 2, and then we give it the host name again, Janelia.org, accepting the standard port, and then we're going to connect. And again, because it's the first time we're connecting, it's saying, I don't know about this. Should I accept its private keys and trust it in the future? And the answer is yes. And here, the one that you're going to want to pick is create a new virtual desktop. And it goes through a few informational slides here as far as how to manage, how you want to have your remote window mapped to the window that's being displayed here. Typically, we're going to resize the remote display to match whatever I'm doing here locally. You can check, after you've decided, you can have it not prompt you with these screens each time that you log in. So that would be typically something that you would do on on a machine once, you know, come on. Important note up here in the corner. Hey, why'd you come back? There we go. So in the upper right-hand corner, if you hover over it, there's a peel back, which then brings up the various options. Let's see. Yes, there we go. Let's see if that'll actually reset. There we go. You're behaving properly. So now what this is a GUI desktop running on login 2. And you can disconnect and reconnect to it, leaving whatever windows are open on. And here's a terminal. So we now have the same kind of terminal that we have had with using PuTTY, but it's running on here, and we can disconnect and reconnect to an existing session.
Rob, how do you feel about using the screen terminal program?
You can do that.
Is it installed on login 1 or 2?
Yeah, screen and what's the other one that's fairly popular?
Yeah, Tmux. John mentioned in the chat. I think I've heard that one used quite a bit.
Yeah. So definitely an option. They definitely have a higher learning curve than this, but you can connect to them with just a terminal, and you don't have to have the full GUI desktop that we're looking at here. So that can be a benefit and a detriment depending on what type of operations that you're running. We're going to take a slight detour for a moment because I want to show you something that is kind of cool. Here we go. So log in to janelia.org. So if you open up a web browser and go to either login 1 or login 2, it will give you a web-based client to access NoMachine. Now, one of the differences is because you're connected to it directly, you'll see all of the various sessions that are currently on it. So you'll have to look and find yours. In this case, it's this one right here. And now it's connected to that same session that I had opened up earlier. Very easy if you happen to be running on a rig that you don't particularly want to install the extra application on, or if you just need to quickly connect, and especially if you're trying to troubleshoot whether there's a problem with your local client and the configuration of the NoMachine client software versus a problem with your session running on the login node directly.
Question. So I think you've already said this implicitly, but for this browser-based version of NoMachine to work, you don't need to install NoMachine on your own computer. You just go to the login1.int.janelia.org and you can connect to a session or create a new one if you hadn't already.
Or create a new one, yes.
I had no idea that you could do this, by the way. That's pretty cool.
So let's see. It was a new feature as of the last rev of the cluster. So a year ago, Christmas time, the winter break, when we did the last OS upgrade, it became a new feature that wasn't a paid add-on. So we enabled it. Okay. Copy and paste is a little interesting there because it has a little bar at the bottom. If you copy something to the clipboard inside of it, it will then show on the bottom of the web browser window a place where you can then copy it out to the actual machine that you're running that web browser on. So it's a little bit quirky that way, but to be able to check on something that's running or just run things, it's really slick.
I think even with the desktop client of No Machine, copy and paste sometimes is different than what you normally expect if you've never used a remote desktop before, because the hotkeys for copy and paste will be different within the No Machine window than without the No Machine window, because you're communicating with a completely different computer in both situations.
Yes.
And so the clipboard, the common space where copied things are stored in memory when you copy them, are in different locations. And so to get that clipboard on the remote computer you're connected to communicate with your local computer, you have to do some extra things. But it's all easily solvable once you get started working with No Machine.
Yeah, and it's very particular to your client operating system. So Windows versus Mac versus Linux, it can definitely play weirdly there. Usually your right click and copy and paste will work consistently. The command keys, Control V, Control C, that kind of thing, or Mac C, whatever they happen to be on your particular one, because on Linux it could be Control Shift and then whatever copy paste key. But once you've done it a few times, you'll figure out which ones don't work for your particular combination. All right, so we hit the NX client. Okay, so now we're going to run a simple job. So I created a directory with all of our examples today. I dropped them out somewhere else so that you can take a look at them. Later, we'll add it to the wiki page for the how-to group. The first one we're going to try out is this. So all this application does is start allocating memory until it's killed, which is in this case, it's a very useful tool to double check that the cluster's memory limits are in effect. It's one that we happen to use for that on a regular basis whenever an update is applied, just to make sure that if you try to allocate more memory than requested, the job gets terminated. This happens to be, this is a B sub file. We'll go into them a little bit more later, but it just collected together a bunch of options into a file. I'm going to translate them into an actual B sub command to submit a job to the cluster. In this case, we're going to run B sub -J. The -J is giving the job a name that's user friendly, or whatever friendly you happen to be. If you don't happen to be a people, you can name them as you see fit. Otherwise, it will default to using the full command line that you pass it as the job name, which may be very long and ugly. The next option we're doing is the number of slots. So N. We'll do a real quick overview of slots here. So what a slot is it is an abstraction of a chunk of a compute node. So in our case, a slot is one CPU core and 15 gigabytes of memory. So basically it is a slice of a compute node, and you can request multiple slices up to the size of a single compute node for a job. And as you request more, you get more CPUs and more memory in total. In this case, I'm asking for 20. So that's going to be 20 CPU cores plus 300 gigabytes of memory. If my application exceeds 300 gigabytes of memory, it'll be terminated automatically. So,
Can I add some clarifications?
yes.
So just for anyone who's never worked in a cluster environment before at all, I want to take a step back and explain what exactly BSub is and where it's coming from. So when you're connected to the cluster, you've connected to one of the login nodes, which Rob mentioned are sort of like the front office. You don't do your work in the front office. It's just where you check in. Where you really want to do all your heavy lifting computing are on the thousands of CPU cores that are available and networked to the login nodes, and that all of those computers are networked together. And when you submit a job, some piece of software has to decide which of those thousands of CPU cores that are available in the data center is your job going to be executed on, and which pieces of RAM does it have access to? How long is it allowed to run? How is that job submission coordinated with many of the other hundreds of job submissions being submitted by other Janelia users? The piece of software doing all of that is called LSF Spectrum, or Spectrum LSF. I don't remember the order.
Spectrum LSF.
Okay. Yeah, it's an IBM product, and it's a cluster manager or a cluster scheduler. Other ones that you may have heard of before are like SGE, Sun Grid Engine, that's a commonly used one, Slurm. So if you've seen those things, LSF is fills the same role as those things do in other clusters. And when you type BSub, you're telling LSF, I want to run the following software with the following resources available. Maybe that was an unnecessary clarification. I'm not sure, but
no, I think that was a great time to bring it in.
Okay.
Rob, and is there any chance you could increase the font size? It's a little bit difficult to see.
Is that better?
Maybe a little bit more, but I think otherwise good.
While Rob is doing that, to connect one of the things he said before to the explanation of LSF, when he said that by saying -N20, requesting 20 slots, that for our cluster turns into 30 gigabytes of RAM. He said, if you exceed that, the job will be killed. LSF is what's going to kill it. It's monitoring at all times how much resources is this job trying to consume. And since this program MEMeter is just going to continuously allocate RAM, eventually it'll exceed 300, and LSF will say, wait, you only requested 300. I'm going to kill this job before it takes over all the memory on the whole cluster. This sounds like a program I would write, by the way.
So the next option up is the hard wall time of the job. In this case, I'm telling it that this job isn't going to run more than 20 minutes. And then by default, when you run a job, it's going to email you whatever would have been printed to the screen, which probably isn't what you're going to want on a regular basis. You're going to want to capture it to a file or discard it completely. But the -O option is what allows you to tell it where to write it. You can either give it an actual file name with a full file path, or you can give it a directory. In this case, I'm just saying write to this current directory, and it will handle naming the log file appropriately. Uses the job ID, which is a unique identifier for each individual job. So it's very easy to map that back to the job that was done. And now we're going to run MEMeter. Okay. And when you hit enter, it hands that off to the cluster schedule that takes a look at what commands you ran, or what options you ran as part of that submission, takes a look at who you are, and then figures out by default who the job should be billed to. In my case, it looked me up and said, hey, Rob, you are in the size comp sys group, and that's who we're going to by default bill it to. And then it looked at some of the geometry of the job, and it picked an appropriate queue based on how long it was running, which is the main criteria that we have for picking which queue to be run in, and then submitted it to it. So in this case, it was submitted to the short queue, and here's our job ID. It outputs it, and the job ID is going to be used whenever you want to look up information on a particular job. So the bjobs command is used to query information about the running, pending, and if you want to, the recently finished jobs. If you run it without any options, it's going to spit back a list of your currently running and pending jobs. The important fields here are, it gives you the job ID, lets you know what state it's in. This will be either run or pen if by default. Tells you which host you happen to submit it from, and then which one of the compute nodes it was assigned to. That's this H07U12. And the number before it is how many slots on that host it was assigned. And then we get information on the job name and when it was actually submitted. And if we want information on just this particular job, we can get that same very short bit of information, or we can ask for a longer version. Ooh, that's rough to see. Okay, so the first sections here are information about the job. We have the job name, who submitted it. The project is the string that we use to decide who the job, what lab the job is going to be billed to. And then it gives us information about what the status is, which queue it was run in, what the actual command was. And then in the next section, we have how many tasks, which were the number of slots requested. It also lets us know what directory this job is going to be run in. In this case, it's my home directory, the how-to directory, and then memtest. And then how much memory was requested by the job and what that cap is. And then as you can see the date stamps on the left-hand side. This was the time that the job was submitted. This was the time the job was started, which was immediately after it, because there happened to be available resources and it didn't have to wait around. And then this last one is, as the job is running, it keeps polling and collecting metrics on the current resource usage. And that's the last time that it was collected. And then we get a little bit more the run limit that we had set. It is listed here, and because we set a hard run limit, we also defaulted the estimated runtime to the same number. And then we get down into the current memory usage. The current max is 56.1 gigabytes, but it will have changed in the intermeeting time since we ran that command, and it's up to 100 gigabytes. Now we're going to swap over to a more interesting tool to take a look at that job. So this is RTM. There's a link on the cluster wiki. It's lsf-rtm.int.janelia.org. And then how we get here is after logging in, we click on cluster, job info, and then details. And then I filtered it down to only show my jobs. And we're going to refresh the page, and we can see the MEM-eater job. Currently, it is at 112 gigabytes of a maximum of 300. We see that there's very little CPU usage because it's just allocating memory. And we can see that the job has been running for almost 5 minutes now. We want to take a look into the job a little bit deeper. The job ID column over here is clickable. I'm opening it in a new window just so that we get to keep that original one, and it's going to load details about this particular job. It does remember which one of these tabs you happen to be on the last time that you looked at the details of a job, so you may have to flip between them. In this case, here's a similar output of the job details that you would have gotten in that B jobs output on the terminal, but formatted a little bit nicer to be able to review. But here's the name, here's the project, here's the queue, similar information. The runtime estimate is over here at 20 minutes. The runtime limit was at 20 minutes also. And here's the working directory that we were talking about. In this case, it fully expanded that $home variable into the actual location of my home directory. But you can also look at job graphs. So these are metrics collected on a 1 minute time slice of what the job was doing. And so this is the amount of memory the job has been using. You can see that it's stair-stepping up each minute. And the job variability is how much it changed within this particular minute. So in this minute, it increased by almost 25 gigabytes for that 1 minute. The next one was about 20 gigabytes for that minute. Depends on how fast it happens to be allocating. But you can see where within your job generally a memory spike was occurring. Back over here. It's getting there.
I have a question.
Yeah.
About something you mentioned before. When you ran the bsub command to submit the job, you included the -o argument so that all of the output, if the program created any output, would go to a directory or a file. And that the default, if you don't provide that -o, is that you get an email.
Yes.
I was wondering, is it possible to get an email when the job status changes, say from penned to run might be useful, or from run to exit or something like that?
Yes, I don't remember them off the top of my head.
But that's more like once you've been using the cluster for a while, if you want to do something kind of more custom like that, just Googling like bsub options and exploring what you find online might answer the question.
Yes.
Okay, cool.
I know that I've sorted that particular one out. I don't know about so by default, it will send the email at the end of the job. There is an option when it starts running the job. That was particularly for an interactive but very large job that was trying to be scheduled. So I know it's possible. I just don't remember what the option was because it's been a couple of years.
Yeah, that's exactly the use case I was thinking of, which is maybe pretty niche. But if you're saying like, I want to run MATLAB interactively, but with 64 cores, which is not huge for our cluster, but big. And
it is large for our cluster because we don't have any 64 core nodes currently.
Oh, that's true. So it would need to be shared across multiple nodes. Does that even work for interactive?
So yes and no. For MATLAB, by default, it would not. you would have to use something like the MATLAB parallel compute server, which would have one main MATLAB engine, and then it spawns off a bunch of workers. And in that case, yes, those are a collection of workers. And the way that MATLAB handles it is it schedules it like a parallel job similar to MPI, because it is using MPI under the hood. So unlike, it isn't going to be a collection of small jobs that get scheduled on their own. It's going to schedule one large multi-node, multi-core job.
Got it. So the max then it would be 48 for something like MATLAB.
Yes.
That reminds me also of something I wanted to clarify before, because this was confusing for me when I first started. There are several terms that I was mixing up when I first started. The terms were node, core, slot, and CPU core to some degree as well. Can you talk about what each of those things are and what their distinctions are really quick?
Sure thing. So a node would be a computer. So it's one physical box, and inside of that machine, so there are going to be a number of processors. In our case, we usually have dual CPU nodes. And then each of those CPUs will have a number of cores. There are actual cores, which is what we equate a slot to, is one actual core. But we also have hyperthreading enabled. So there, for every physical core, it has two logical cores assigned to it. So that in the case of non-highly compute bound tasks, it can swap between those two and better use that CPU core. If you're doing heavy math, it's still going to use all of that core, and you aren't going to be able to get twice as much floating point math out of a single core with hyperthreading. But if you're doing a lot of I/O operations, that's usually where we see a lot of help. There is an I/O operation can be blocking on one logical core, but the other logical core can get in and use the underlying actual compute power while it's waiting for that I/O operation to finish. Did I hit all of the pieces? So
I think so. So we had node is an actual computer with physical CPUs on it.
yes.
And then there are many nodes networked together that makes up the cluster. And a CPU can have multiple cores, and each of those cores can have hyperthreading enabled, which means that it's more than that. It is a single physical CPU core, but because of some smart tricks at the operating system level or kernel level, I guess, it can interleave multiple two streams of computation, which is more useful for input output than for mathematical stuff. But node, computer, CPU, physical CPU object made up of multiple cores, and then slot is really an abstraction, but for us, it means one physical CPU core and 15 gigabytes of RAM.
Correct.
Okay, great.
Ken, what was your question?
That was Zoom deciding my hand was raised. Sorry.
No worries. So we'll go take a look back.
Sorry to derail you for just another second, Rob. I just want to mention that Eric found the answer to my question. The specific BSIP flag is -notify. So if you submit a job and you want to know more about how the job state is changing, let's say the cluster is very busy, which is not super frequent for us, but it can be the case sometimes. And you want to know, I submitted a job and I want to know when it actually starts running so I can come back to my computer and look at real-time output or something, then you could provide -notify and read the documentation about that flag to learn how to get an email, like when it changes from pending to run state, for example. Then you might know, like, your coffee break's over, it's time to go back and look at the output of your job.
So one important note about the email notifications. There is a restriction that it will only send emails to a user at janelia.hhmi.org email address. It won't send it to a user at hhmi.org, and it won't send it to an external email. That's a concession that we have with the email security team. That because because there isn't an auth involved in sending the email, to prove that you are who you are, it's just accepting the emails. We only send them to internal addresses.
That makes complete sense from a security standpoint, I think. Yeah.
Yeah, it doesn't affect the majority of full-time employees, but it can affect the remote research collaborators or some visitors. So, and by default, it sends it to whatever your username is at janelia.hhmi.org, or rather whatever the username of the account that's running things. So in the case of some of the project accounts, let's take FlyEM, for example, that may be black-holed if there isn't a FlyEM at janelia.hhmi.org email address that exists. Okay, so let's check in on that MemEater job. And it has finished. So we're gonna take a look down through the state changes. We had that started at 10:35. And then at 10:47, it exited. And then we get more information on why it exited. And in this case, it is because it was terminated due to exceeding its memory. So it's captured in this information, so you can see that it occurred. There are two ways that a job can finish. Well, two states that they can be in when they finish. One is exit, which means some sort of an error was captured. In this case, it was because it ran over its memory. It could be because the person chose to kill the job early, or it could be because the application itself finished and returned an exit code of some sort, other than 0. Now, in some cases, applications can return exit codes meaning various things based on what the exit code was, but it's still completed. The application feels it's completed successfully. So you may have to look at your individual application. There was an internally built application that for a while, it exited with an exit code of 42 because it was the answer to everything in the universe. But it also meant that all of those jobs looked like they had terminated with an error, even though they really hadn't. The other state that it can finish in is done. And and done means that it ran to some form of completion and didn't return an error code before the application finished. There is also another exit code that is the job exceeded its runtime limit, and it will say term run limit instead of term mem limit. All right. Let's go on to our next. So here what we have is an input file that happens to be a very large tar file with a bunch of junk in it. And these are 5 different variations of effectively the same operation. They're all requesting 6 slots, but with varying threading settings on them, everywhere from 1 thread up to 12 threads. We'll take a look at one of these. I just jammed them into individual files so that it was easier to keep track of all of the arguments that I was using for them. So more sub. So what we're doing is we're submitting a job. we're naming it 12 threads, 6 slots, giving it a wall time of 60 minutes. We are requesting 6 slots, specifically dumping the output, the terminal output to the current directory. And then we're running this, which is basically we're going to time how long it takes to parallel bzip this with 12 threads, and then a few various other options that mean I don't have to regenerate the input file each time.
And just a clarification here, everything that's in quotes after the -o./ everything that's in quotes after that, that's your code. That's like what LSF is going to execute. So that could be Python space Python script. That could be an executable that you compiled in Java or C++. That could be MATLAB something. It could even just be a bash command. But in this case, it is, I want to time the execution of the pbzip2 executable, and then all of the flags after that are arguments to pbzip2. They're not arguments to LSF.
So, 12. Because I put them in a file fully formatted and made those files executable, I can just execute it and it will then run the command inside of the file. And now the jobs. So a handy flag for the bjobs command is -w, which is wide, so that it will then expand those job names. If you see a star at the beginning of any entry in the bjobs output, it means there's more here. It was just truncated to fit the formatting that was applied. So now we can see that I have these 5 jobs all running. 2 of them ended up in the cloud queue because I set slightly longer runtimes because I ran these yesterday, and the 1 and the 2 thread version happened to take slightly longer than an hour. The other ones finish in less than an hour. But based on setting that runtime is what allowed the scheduler to decide which queue it was going to automatically put them in. Because 3 of them finish in less than an hour, they were assigned to the short queue, which is jobs that you tell it are going to run less than an hour can run there. That queue happens to be very large. It spills over onto lots of nodes, and that can happen because at most we're looking at an hour before the jobs clean up, and that's a reasonable amount of time to be inconvenienced if by some chance the cluster got filled up with such jobs. Similarly, the cloud queue would be anything between 1 hour and 4 hours. And again, it can spill over into more nodes than the default queue, which is called local. The local queue has a runtime limit by default. If you don't apply any run limit to your job and it ends up in the local queue, it's a 30-day limit, mainly because the queue has to have some limit of, it has to have some limit applied. And we picked 30 days because anything that runs longer than 30 days, you should probably have a conversation with us first. And we should figure out whether or not the application can be sped up, because 30 days is a very long time to have all of the hosts up and not have something interrupt in the middle. And it would really, it would be awful to get to 29 days and have your process die for some reason and lose 29 days worth of processing. So if you do have something that you expect is going to take longer than that, it's a conversation that we should have to figure out why and if there's any way we can speed it up.
And there are usually good options for that. Parallelization, breaking the job up into separate jobs, writing intermediate outputs. GPU acceleration, there's usually a solution. I don't know of anything that we've run that takes longer than 30 days. Even like the big fly EM assemblies and stuff don't usually take that long. But I suppose, have you guys had that happen before in the history of Janelia?
No. Realistically, no. Anytime that we
challenge accepted.
So at any point that somebody had a job that actually hit the 30-day limit, it was because the job misbehaved and they lost track of it. I have never had somebody that hit the 30-day limit and the job was really doing what it should have been doing and couldn't be sped up in some other way.
And if I can add one more clarification, can you go back to the terminal window really quick while I mention,
Yes.
just I want to take a step back and talk about queues more generally. So you gave us a good list of some of the queues that are available and what they signify, but I just want to say what a queue is. So when you interact with LSF, when you submit a job to LSF, it determines, what resources that job will be run on, that can be impacted by what queue you specify, which line the job gets in according to LSF. And the queue that you choose can, as Rob mentioned, impact whether it's run on local hardware or on cloud-based hardware. Although if you submit to the cloud queue, it's still most likely going to run on local hardware unless the cluster is very busy and some cloud nodes have been enabled. But there are also queues for GPUs, for example. If you want to use a GPU, then you have to submit your job to a GPU queue. And there's great documentation about how to do that in the cluster wiki. But one of the flags to the bsub command is -q, the letter Q, and you can manually specify which queue you want to put your job in. And when you are submitting more complex jobs that require specific run times or specific hardware, or that it's a quick job and you want it to be able to run without having to wait for longer jobs that have been submitted, then your choice of queue has a lot of impact. So you'll want to read the documentation about those queues and how to select them when you get to the point of submitting jobs with that level of complexity.
So we're going to take a look at the jobs that I submitted. Here they are. Let's maybe sort by job name. But so this column is the total number. Unfortunately, because LSF and the tooling around it are generic to many, many different sites, sometimes terms are overloaded or conflated. In this case, the number of CPUs is actually the number of slots. So all of our jobs here requested 6 slots, and by default, we assume that your job is going to run on a single node because you have to write code that is smart enough to handle message passing and communication between multiple nodes to be able to actually schedule a job that is distributed across multiple nodes. So by default, we happen to set that all jobs coming in are going to run on a single node and allocate slots on a single node. That is different from other places. A place that runs lots of large simulations will default to distributing those over multiple nodes. And then you have to ask for all of your cores to be scheduled on a single node. It's a slight difference. It's based on the primary type of jobs that are being run on a site as to deciding which is going to be your default. And so we have the amount of CPU time that each of these jobs has run, and we can see that they're very different depending on the number of threads that were generated. And the core efficiency is the amount of CPU time run divided by the amount of total wall time in slots. So the total wall time, so time since the job started, it's been running for 5 minutes, times the number of slots that were requested. So there were 30 minutes of available um, 30 minutes of available wall time based on or slot wall time. And then we're going to take how much actual CPU time and divide it by that. So in the case of our 12 threads, 6 slots, so it was generating 2 threads for every physical CPU core. That one happens to be running at 180% because of the hyperthread. This application happens to be able to take advantage of it because it's a combination of a lot of I/O, because it's reading and writing the chunks of the file. And it also has a fair amount of computation involved because it's calculating those similarities for the compression. It just, which is why I use it as an example, because it fairly well shows how to fully utilize both the CPU and the additional logical cores. But this will, if you take a look at these, you can decide which, if you're testing them, you can decide which one actually makes the most sense. I mean, because you may get to the point where the application is thrashing too much and it isn't able to really utilize those, and it's spending a lot of time swapping the code in and out of the CPU. And or on the other hand, you may look at it and go, man, I probably shouldn't have requested, I shouldn't have only ran 2 threads with those 6 cores. Unless, on the other hand, you need the memory. Because we lump those together into slices, there are times that you may need to request more slots than you have CPU work to do just to get the memory to cover your application.
Often that means because you had to, your rate limiting step was memory, and that determined how many cores you have. That can coincidentally mean that, well, I can turn up the threading if there's an option for doing that, and maybe get the job done a little bit faster too. And about your comment regarding the thrashing, so the largest number of threads you ran with here was 12, because you have 6 CPU cores and hyperthreading is enabled, and so you have 6 logical CPU or 12 logical CPU cores, and the operation contains a lot of I/O, so hyperthreading would be useful for those parts of it. If you had submitted with, say, 36 threads, then the computer will do that. It will submit those 36 threads, and it will attempt to coordinate all of that work on those 6 CPU cores. But, and you said all of this, but it took me a while to understand this myself. When overthreading a core like that, the operating system is going to spend a bunch of time saying, all right, I'm computing thread A and then switching to thread B and then switching to thread C, and all of that additional overhead of constantly swapping in and out what the CPU core is doing will actually reduce the efficiency of the job and eventually could grind it to a halt and cause it to crash. And so I think you didn't submit a job with 24 threads because it would be a bad idea to do that. But sometimes that can happen by accident, and it's important to understand and notice what the symptoms of that are. And this can happen by accident because often we're using packages that are themselves multi-threaded and you may not be aware. So even if you're just using NumPy and Python, for example, under the hood, that's very well multi-threaded. If you're writing something on top of that and you multi-thread it yourself, then you may be spawning too many threads for the number of slots that you have. And so noticing if your core efficiency ever goes above a certain percentage, or if your job is dying in an inexplicable way, then it could be because there's too many threads. And that's one thing to look into.
Well, and another thing about the various Python packages, so if you aren't passing it environment variables to control those various NumPy threads, it will typically look at the total host. It isn't, those packages are not scheduler aware. Like, they won't look at the job information and say, this job only requested 6 slots. It will look at the total host and use that to determine how much threading it should do, which is even worse if they assumed that you were going to run it on a machine that didn't have hyper-threading enabled, because a lot of the NumPy operations are heavily math. Like they're going to fully utilize the core that they're run on. So it will actually look even worse, because it'll interrogate the host and say, oh, I have 96 cores. But
Yeah,
there
it's
are
looking
only
at the whole
48
node.
cores. Yeah.
Yeah, it's looking at the whole node in that case and assuming hyperthreading. But
Or-
as you said, it's not aware that like out of those 48 physical CPU cores, or sorry, what did I say? 48, right?
Yep.
48 physical CPU cores, the scheduler is only allowing you access to 6 because that's what you were requested. It doesn't know that. But there are ways to get it in Python code itself. I think psutil.cpu count will give the right amount. And you can look at there are environment variables that are set by LSF at the time you run the job, which are probably better to look at because they're set by LSF. That tell you the true number of CPUs the cluster is giving you.
Yep. All right, so we're going to let those continue to run. But running multiple iterations of a small chunk of your data set can be very helpful to decide what in a very large scale you should be picking for your job sizes and run times, etc. Oftentimes it will be very useful to request an entire node to then run a small chunk of your processing to be able to then watch it and see without it interacting with anybody else's code on the node what you really need. I mean, there may still be interactions when you start shrinking it down as far as how it's sharing with other people, but it's a good place to start. And that leads us to how do we test out some code? And
I said something totally incorrect a second ago. Just want to make sure it's on the record. psutil CPU count does not give the right CPU number. I just tested it. It gives the full node count number. So you want to look at the LSF specific environment variables in a job to get the true number of CPUs your job has access to.
Yeah, it's all capital letters, djob_num_procs, I think. It's documented on the wiki page in the section where you see a table. Let's see, I have the wiki page. Let's go look at it. Here we go. We have this handy dandy chart because once upon a day, the numbers were not quite as easy to multiply as 15. Back in the days of 7.5 and 6 and various, it was definitely much harder. But LSB_djob_numproc. That will give you back the number of slots that the job requested. Okay, so next we're going to do a quick, I want to run some things, but I shouldn't run them on the login link. So there are two different kind of classes of jobs. There are batch jobs, which are, here's a command, scheduler, please go run it somewhere else. You handle everything and it's going to generate some results. It's going to save whatever would have been printed to the terminal to a file, and I'll go look at it later. So that's a batch job. You can submit many thousands of those, and it's kind of a fire and forget. Like, hey, just run. The other type would be an interactive job, which is I am going to need to provide information or commands or something during the course of running this application. Very common for that would be running MATLAB or running any other application that has a GUI, but MATLAB happens to be a very simple one. So we need to submit an interactive job. To do that, it's still dsub, and we're going to request the number of slots. In this case, I'm going to request 16 because it gives me a nice large amount of memory and enough CPU cores. You can adjust it to whatever you need for the actual application, but remember that the memory limits still are in effect here. So make sure that you request enough to cover whatever you're going to run. And then IS, and what it's saying is I'm going to run an interactive job with the shell being bash. So this is the command that I want you to run. Bash happens to be a shell. And You wait after it, you wait for it to be dispatched. It's going to start. In my case, the only thing that I have in my startup files, bash RC and bash profile, is really to run the host name so that I know where I'm on at any given time. Not necessarily for the cluster specifically, but because it's very handy when I'm dealing with lots of different hosts, managing them. So we are now on this compute node. We can see that it has this different name than when we were on login 1. And the jobs, it shows up differently here. It's in this interactive queue, which we have a couple of dedicated nodes that only interactive jobs can be run on, but the interactive queues can be scheduled to the various other CPU nodes that are available for batch jobs. So you're not really confining yourself, but we have some reserved resources so that even when the cluster is very, very full, hopefully you'll be able to get a job schedule.
Would this be a useful time to look at cluster-status?
Sure.
This website really has helped me understand like what's happening with my submitted jobs. It just gives me a visualization of like where things are located. And like when Rob submitted this interactive job and highlighted the host it's being run on, you can see this physically or in a cartoon form like this from this website, cluster-status.int.janelia.org.
So this page gives a general overview of what's happening at the moment. We've got everybody that has jobs running or pending, and then how many of those jobs there are in both of those states, as well as the number of slots that they have in use and the number of GPUs that they have in use. And then we've got these cute little heat bars as far as in total, how much of the cluster slots are being used and how much of the total cluster GPUs are being used. Also keep an eye out down here whenever we do any kind of maintenances or there's something going on that's odd, we'll add notes here. It's a really good way to check very quickly, is there something that I should know about that's happening without having to email somebody or submit a ticket, because there could be a lag there. If we're going to be doing, we try to be very conscientious of how many emails that we send out to the cluster users email distribution list, because there are 400 odd people on it. We don't want to be sending out emails on a daily basis because then they won't be paid attention to because there's too much noise. So instead, it's more of a pull for information rather than us pushing information at everybody. And so this cool visualization, if you click on enlarge, it will show you it in a much larger format. So what these are is each of the hosts, or each of the compute nodes in the cluster are listed with their host name. And then each of the little boxes is a slot. And so we keep track of how many slots on a particular node a particular person is using. And that is then mapped to this. We are not tracking which actual physical cores you happen to be assigned to, because it makes this very long to compute and display. It's updated every 30 seconds, so you can get a pretty good idea of what the current state is and who is running what where. The little circles are the GPUs in the node, and you can see who, if you hover over it, you can see who happens to be scheduled to that. And in this case, it's Will. And if you come down to the bottom, you can hover over a particular name and it'll highlight all of their slots and GPUs that are in use up above.
So where's your job?
Let's see.
Like lower H07U31 is where some of the decompression jobs are running, maybe.
Yeah, so that does look like it. Yep, HO7U31 looks like the decompression or the compression jobs, and 7U01 is where the interactive lab happens to be. So those first two nodes on the left-hand side are the interactive nodes. We specifically spread them across two racks. The naming nomenclature is actually the physical location in the data center. The letter at the beginning is what row in the data center it happens to live in. The first number is the rack within that row, and then the last number is what unit within the rack it's located in. So that we can find it in a much easier manner than trying to keep track of like naming them after historical figures or scientists or pizza toppings. I've seen all of these, and it wasn't until I saw this naming that I really appreciated it. And so they're kind of broken up into the top group here are the primarily CPU jobs. So that's the local, cloud, and short. This next section, these hosts happen to be off at the moment. Oracle is who we use as our cloud provider for bursting to the cloud for the cluster. When they are online, they'll have slots that show up just like any of these other compute nodes. The cloud queue will expand to use them if they're online. And then down below, we have the various types of GPUs. V100s, A100s, RTX 8000s, and then the RTX 2080 Ti gamer cards. And each of those has their own unique GPU queue associated with them to pick what type of GPU you need. And then you do have to specify how many GPUs you want to be assigned, and it has to be enough. It has to be a number that would fit within a single node by default. And all of the CPU, primarily CPU nodes, do also have a Tesla T4 card in them for a very heavy compute workload that has a small amount of GPU accelerated work to be done. Now, the layout of this and the hardware that's available may change by the time you're looking at this video, assuming that it's more than 6 months out down the road, because the hardware that we have is fairly constantly changing as money becomes available and as things die or age out. So take a look at the wiki. There are all of the various types of GPUs that are currently available are listed there. And they also have a mapping of how much GPU compute, theoretical compute capacity those cards have, as well as the slot to GPU ratio to try to align with, to avoid stranding GPUs. Because if you take a look down here, the only thing that could fit in this particular node is a GPU job that's requesting 2 slots and 1 GPU, which we have. But if it's requesting more than the average 5 slots per GPU, and there are a lot of those jobs, it's very possible that we could have GPUs stranded, and those happen to be one of the resources that are not cost effective to burst to the cloud to expand.
I just wanted to, at this point, make sure, because we're a little bit over and I've made a lot of interruptions, that's totally my fault. But just to make sure that people feel comfortable leaving if they have other meetings or if they need to go, unless there are any objections to that, I will stay until we cover 100% of the material and have good documentation. But just so that people are aware, I am noticing the time, and I'm not offended if people have to duck out.
John, what's up?
Yeah, that'd be great. I've got a quick question about the cloud queue, if that's cool, if now is an okay time since it's come up a couple times.
Yeah,
Awesome.
let's talk about it.
Yeah. So I guess my question is for like if jobs, how does the data that a job needs to work on get shipped to the cloud? And I guess, is there a way to distinguish between jobs that take a small amount of data and a lot of compute versus jobs that do a like small amount of compute on a lot of data over and over again, if that makes sense?
Okay. So the simple answer is the data is just read off of the same file shares, because all of our compute nodes in the cloud are running the exact same OS image as we run locally, effectively. There are a few very minor tweaks because they don't have the exact same network cards at the other end, and they can't support RDMA when crossing that interconnect boundary between us and the cloud. But all of the shares are still mounted in the same location, so the same data is available. Your home directory is mounted. They do happen to be AMD based, so AVX 512 instructions don't happen to be available, but you'll read data the same as you would on a local compute node. And up to a certain degree, it's going to be basically the same. There are some, I mean, you're going to hit some bottleneck if you have a very, very high IO operation that needs a lot of bandwidth, because there is only 100 gig interconnect between the Janelia data center and the cloud at the moment. So, I mean, but it is 100 gigabits. So it's not slow, but by default, we have up to 64 that we can turn on with basically running a single command, assuming that the resources exist in the cloud at that particular time to be able to get the fairly large nodes that we're requesting. But 64 50 gigabit clients is a lot more than 100 gigabits. So that being said, if you did have a very latency sensitive and high bandwidth IO job, then making sure that it didn't end up in the cloud queue would be appropriate. And you could do that by specifying. So even if you specify a runtime that would by default land it in either the short or the cloud queue, you can include also a specific request for the local queue with that -q local and say, I know that my job looks like it's a candidate for going to the cloud, but don't run it locally. So that would be the workaround.
Yeah, that's super helpful. Thanks.
Just a point of curiosity, and I know that it doesn't matter for the compute ultimately, but do you know where physically these cores are located when they get allocated by Oracle? Is it like a data center nearby, or like
yeah, it's in Reston.
Oh, okay, cool.
Yep, it's down off of Sunrise Valley Drive, and our direct connect is from the Janelia campus directly to whatever their POP is there in that data center building. So it's very close. I mean, it's close in terms of the internet. Now we're talking about an order of magnitude difference in latency between running just inside of the Janelia data center versus going out there. So yes, a latency sensitive application would be one not to necessarily spin out to the cloud, but you can pick that. And
but you're talking about
yeah,
and you're talking about jobs in that case that would need to send hundreds and hundreds of gigabytes or terabytes of data to the compute nodes in RAM. Like those are the types of limits we're talking about, right? Like even if you're running something that's 200, 300 gigabytes, the total IO relative to your compute time is probably not a concern for cloud node.
Yeah, assuming that you have a fairly long runtime, even if you are loading a large amount of data over the long term, it's going to be fine. It would be a job that is doing a very large amount of IO and very little compute, and those exist. I probably wouldn't, and I would encourage not running like an N5 conversion type job on the cloud. That should probably be run locally, but I mean, it still could, but that would be a very low CPU, high IO operation, and it would just finish faster running within the data center at Janelia.
Yeah, those types of jobs definitely do exist here. But I think if you have one, you'll know it's not something to be super worried about, and like you'll know that you're running a job like that before you run it.
Yeah, well, and if we see it, we're going to have a chat with you and say, you know, we saw this. Is this what you're trying to do, and how can we make it better? Because we do keep an eye on that whenever we do spin up cloud resources, we keep an eye on the interconnect link to see, are we oversaturating it? Because I mean, it is 100 gigs sounds like it's really fast, except that, you know, on a local basis, we have many hundreds of gigabit connections between the compute racks and storage. So, you know, so at this point, the typical compute rack, we are uplinking with 800 gigabits out of each compute rack. There is a little bit of overlap for some of the GPU racks, just because there aren't very many nodes in a single rack. So they may have two adjacent racks sharing a top of rack switch, but still we're talking about very large bandwidth that it's just not, it's not reasonably possible to get to the cloud, but at the same time, spawning off the jobs that aren't so IO intense to cloud nodes can free up the local resources. All right. That's RTM, we've looked at those. All right, so here's our interactive job. We've got, what do we still got one? The one thread, 6 slots. As expected, it's going to take about an hour to run, because that's how long it takes to compress that 45 gig file down to 27-ish gigs with a single thread. So now this terminal is running on a compute node, and it's forwarding back the contents of the terminal to this terminal window that's on a login node. Now, the cool thing about this is it has set up by default an X Windows session to forward graphical applications. And local. So Misk Local happens to just be a share where we install various software that has been built on the cluster for use on the cluster. It may work elsewhere, but we only guarantee that it's going to work on the cluster nodes because that's where we built it, and that's where the various shared libraries are going to exist. And typically we'll have a file in each of the folders. Yes. So here are the various applications that are installed there. The standard format is application name and then the version of it. So you can take a look there to see this is where anything that had to be built that wasn't included with the operating system itself will be built.
Hey, Rob, I get the sense that the next thing you're going to show is how to run MATLAB and then how to run Jupyter notebooks, just based on what was in your folder.
Yeah.
Can we do it in a subsequent session? I definitely
Sure.
want to document that, but I said this in a meeting the other day. People will watch a whole series of episodes on Netflix, but they won't watch a 3-hour movie, right? So like breaking it into chunks, I think is more consumable and easier to share. I'm sorry, I know that I'm the one who created most of the delay in your
No
presentation.
worries.
So if you're willing to come back a second time, then we can do specifically running applications of interest session.
Yeah, definitely.
Is that good? Okay, cool.
Yeah.
Then I'll let you do whatever other things you want to wrap up that doesn't include MATLAB and Jupyter, and then we can email to schedule a second one. This, by the way, was amazing, and I learned a bunch of things I didn't know. I've never used the dash lowercase l for B jobs, which is super helpful. I always just go to RTM, and I'd much rather just do it in the terminal. And then
So it's a trade-off. The dash L is it will only show you jobs that are running, pending, or recently completed. Now, recently is a sliding scale based on where we are in our maintenance windows. Typically, it's set at about 48 hours. If we happen to be working on maintenance for either the cluster or RTM, we may extend that, how long it keeps recent jobs in memory, to a longer period of time. Basically, as long as the job is in memory, it makes it really easy to suck that data into RTM. The minute that it gets purged, it's a very long process because it has to reread a bunch of logging files. So that's the reason that we have the 48 hours of recent jobs in memory still, is so that if something happens to RTM, we can recover very easily. Particularly because we have a very high churn rate of jobs. We average anywhere between 100,000 and 300,000 jobs a day, and a million job day is not out of the realm of possibility. We get them on a fairly regular basis, whereas the tools were really originally designed for the very large simulations where you're running a small number of jobs. So reprocessing a small file is easy. Reprocessing a multi-gigabyte file of logging events is time consuming.
That makes sense what you just said so much to me, because RTM is extremely useful, but it is a little bit laggy when you hit go, and that you guys have made good choices about how much logging to keep, but that makes complete sense that IBM designed it for a NAT lab that has maybe 5 users of the cluster who are submitting one job every other day, but it runs for 48 hours, and it's a single job.
So RTM, we're expecting to replace the hardware that it's on later this year, whenever some larger collection of machines is purchased, we'll be sliding the replacement hardware for it into that so that we get the discount of a larger order. And hopefully the current one is running off of SAS SSDs. We're hoping that moving to NVMe and a few more cores will make it a bit more snappy. A bit of that was just their move to using Ajax instead of generated pages. So we'll see. But I do encourage using
useful. And like what you said, for looking at jobs, which I don't want to admit how often I have to do this, but looking at jobs that exited or failed, it's RTM that I got to look at.
Yeah. The columns and the amount of information that you can add in the form of the various columns is incredibly powerful to be able to see a summary that is very hard. Like, you could get similar information using the bjobs command, but you'd have to form a very complex collection of options to get it to format the same amount of information that RTM shows in a graph.
And probably grep it in all kinds of weird ways to get it to actually show you comparisons between jobs and things that you can just format through GUI options in RTM.
One other note about running bjobs. Running watch bjobs sounds like a great idea. It's really too frequent, and it's not going to give you the amount of information that you want compared to the added stress that it puts on depending on how many jobs you're running. The information that bjobs returns is actually a cached version of the current state, and that only updates every 15 seconds or so, depending on where you are in the update cycle and how many jobs there are in the scheduler total. So running watch with a slightly longer time frame, because the default is 2 seconds. If you use the option is -N, I think it changes it to 15 seconds, 30 seconds, a minute would be a much more reasonable time frame. That way you're not just hammering the scheduler asking for the same information that hasn't changed and won't have changed just because it hasn't updated that cache in the time frame.
That's more Jedi and I'm more Padawan. I just run B jobs one at a time to look at this job, that job.
That is totally fair. And in that case, you're not going to overload the scheduler because it's going to take you longer to read it. It'd be more the running watch and then leaving it sit and going off on vacation. Then that's kind of wasted cycles that the scheduler could be spending on picking how things should go and deciding when things are going to be run.
Yeah, the scheduler is busy. I don't want to be nagging it all the time.
Awesome. We'll connect and set up a future session to talk about MATLAB, both the IDE and running it on the command line, as well as starting up and running Jupyter notebooks. And if anybody else has applications that they would like to see talked about, I definitely drop them in the Slack, the how-to Slack, and we'll see about integrating them into that talk.
That's perfect. Do you want me to write a request for those suggestions, or do you want to do that in the how-to? I'll
No.
post. I would post in the how-to Slack and the just general Janelia scientific software, because I'm trying to pull more people into the how-to Slack. But that's a good question, because like those are the two things that jump out in my mind is like new postdoc, new grad student probably wants to run them, but maybe there's other stuff too. Yeah. But yeah, thanks so much for doing this. And like, this would have sped me up by 6 weeks if I'd had this video when I first came to Janelia. And I know that SciComp is talking about hiring rounds soon, and this will definitely be viewed by, people coming in as like, this is the first thing you watch to get going on the cluster. And so tremendous job. And we're grateful to like learn from you, and thanks for doing this.
What's up, John?
Just expressing thanks. Thanks, Rob.
Cool.
Yeah, thanks. This was great, and I look forward to the next session as well. So.
Awesome.
Okay, see you guys soon. Bye.